All right, these are the slides on momentum and impulse. So the original question is, what is the rocket sled challenge? So this is how we open up the concept of momentum. So the goal of the rocket sled challenge is to launch the front of three carts as far as possible. The challenge will consist of three launches over the next few weeks. The team that launches the front cart the furthest on that third launch is the winner. So you can see here there's three carts lined up, and that front cart is the one that you care about. And you can see that the students here are already lining up to push the carts. So the rules for the first launch: your goal is to make the first stage have the furthest launch distance in the class. So you use three human dynamic carts, and these are basically the rules for that. So you can read over them, but essentially what it is, it's designed to set up to where, well, the carts are going to be isolated, right? So this is like a rocket. That front cart is like the payload that you want to go the furthest, and the fastest, the back carts are like the different stages. All right. So the first conclusion questions that you're asked are to come up with a good team name, the team, and the strategy to get the front cart to go the farthest. And then you're going to have to decide where those students were going in order to get that front cart to go the farthest. So after the launch, you ask, how far did the rockets let go? What part of your launch strategy worked well? What went wrong? And how will your team adjust strategy for the next part? So right now we know nothing about momentum. We just did a launch to see how it does, and these were the results. You can see here some of them were good, some of them weren't so good, but overall, like, nobody went over like 9 meters, so nobody went like more than 9 feet. So in order to get better at this, we need to learn the concept of momentum. So we know that all objects in motion remain in motion in a straight line, and this property of a body to keep moving has a special name. It's called momentum, right? So momentum depends not only how much mass, but also how fast that mass is moving. Now, momentum is the product of mass and velocity. It's a vector quantity, which means it has both magnitude and direction. So the momentum is kilogram meters per second. So let's look at a bowling ball versus a tennis ball. So which of these objects is going to resist change in motion more? So the one that's going to resist change in motion more is going to be the bowling ball. If you were to toss it back and forth, you would definitely feel that resistance more. Which object has more inertia? Well, we know that we measure resistance to change in motion with or is inertia. That is inertia, right? And which object has more mass? These are all three the same questions, right? So resistance to change in motion is inertia, and we measure inertia with mass. So the bowling ball has more of all three of those. Now, what would you need to know in order to answer the question, which object has more momentum? So the bowling ball will always have more inertia, but momentum depends on an object's velocity. If an object is at rest, that object does not have momentum. So the last question is, under what condition could the tennis ball have more momentum than the bowling ball? Well, if the bowling ball isn't moving and the tennis ball is moving, well, then the tennis ball would have more momentum. So now let's talk about how we get momentum. So how does one get momentum to start with? How does one lose the momentum already has? And in other words, what does it take to change one's momentum? So if we're going to change the velocity, a net force must be applied. This is Newton's first law. Now, to produce a change in momentum, you have to apply what's called an impulse. Impulse is change in momentum. So the calculation for impulse is the force applied multiplied by the time interval the force is applied. Or if we write it mathematically, impulse equals force times delta t. But impulse does also equal change in momentum. So change impulse is mass times change in velocity. So you get, if your velocity gets faster, your momentum increases. If your velocity gets lower, well, then your velocity is going to decrease. Now, what I want you to look at is, if you put it all together, those equations on the right are all the same. So you notice change in momentum equals mass times change in velocity. Well, we know that impulse is change in momentum, and impulse is the force times the time that that impulse is applied. And then that last part is just expanded out. So the final velocity minus the initial velocity. So let's look at some components to impulse. So impulses always occur in pairs. Impulse pairs are always equal in magnitude. Impulse pairs are always oppositely directed. Impulse pairs are always simultaneous. Impulse pairs never cancel because they act on two different bodies. These should look very similar to the same components of Newton's third law, those force pairs. So let's take a look at what this means. So let's look at the golf ball, right? So Newton's third law tells us that there's a force acting on the ball and a force acting on the wall. So which of these objects exerts a larger force and magnitude to the other object? Well, Newton's third law says, well, they're going to be equal. The ball is going to hit the wall is going to apply an opposite and equal force right back. Which object applied the force first? Well, force pairs are simultaneous. They happen at the same time. which object applied the force for a longer period of time? Well, they're simultaneous, so they happen for the same amount of time. Now, if these forces are equal and opposite, why don't they cancel out? They act on two different objects. Now, this one's kind of tricky here, right? Which object, if either, experiences a larger impulse? Well, impulse is force times the time that that force is applied. So we've already established that the forces are equal, and we've already established that the time interval that they're applied is equal. So, well, if the forces and the time interval is equal, then the impulse must be equal, because that's how you calculate impulse. And this next question says, which object experiences a larger change in momentum? Well, if the impulses are the same, well, then the change in momentum must be the same, because the definition for impulse is change in momentum. But let's look at this last part, though. Why is the effect of the same impulse different on the different objects? So let's take a look at this. We know that the forces are opposite and equal. We know those forces are applied for the same amount of time. So the impulses applied to each are the same. However, that wall, since change in momentum is two different variables, that wall has a lot more mass than the wall. So the velocity, change of velocity is going to be low, as opposed to the golf ball, which has a small mass and the change of velocity is going to be higher. So let's take a look at this even further with that bungee lab. So in this one, we just loop the bungee cord around the thumb screw and you drop the empty soda bottle from the top of the clamp using the bungee cord. Describe what you notice about the force applied to the bottle when the bungee cord brings it to rest. Then you do the same thing with that nylon static rope. So if you're looking at these conclusion questions, well, here's one. In which of these scenarios, the bungee cord or that static nylon rope, does that bottle have a larger mass? It's the same bottle, so the same mass. Now let's look at this one. In which of these scenarios does the bottle experience a larger change in velocity? Well, it's going to be the same change in velocity, because assuming it's the same bottle from the same height, the end result is that it comes to rest. So it's going, it's moving down, and then it comes to rest. So both of these stop that. So now let's answer those rest of the conclusion questions by answering other questions here. Why do people bend their knees when landing? So if we look at bending your knee versus landing, so in which of these scenarios does the person experience a larger change of velocity? It's going to be the same. Just like that bungee lab, it's going to be the same, because either way, you're going to come to rest. In which of these scenarios does the person experience a larger change in momentum? Assuming it's the same person falling from the same height, well, the change in momentum is going to be the same, because the end result is going to be the same. So, in which of these scenarios does that person experience a larger impulse? Well, we know that the mass is the same. We know that the change of momentum is the same. The change of momentum is impulse, so it's going to be the same impulse. Now, in which of these scenarios does that person take a longer time to come to rest? It's going to be bending your knees, right? So, in which scenario does that person experience a larger force? It's going to be if they landed with their knees straight out. So, which variable does bending the knees increase? Which of those, either force or the time applied? It's going to increase the time that that force is applied. What it's doing is it's spreading that force out over a longer period of time. But what does that do to the force? So let's look at this. Which variable does bending the knees decrease? Well, if you're experiencing that force over a longer period of time, well, it spreads it out. So you're going to experience a less force for a longer period of time. So like same person, so same end result. They come to rest, same momentum, same impulse. However, since impulse is two different variables, well, what bending your knees does is it spreads that force out over a longer period of time. So let's look at a bungee rope versus a static rope. So which of these scenarios does that person experience a larger change in velocity? Well, either way, assuming the same person falling from the same height, it's going to be the same, because either way they come to rest, right? So that's somebody bungee jumping, and that's a clip from the Mummy movie. So don't worry, he's okay. He goes on to two other sequels. So, but either way, those chords brought them to rest. In which scenario does that person experience a larger change in momentum? So, assuming it's the same person falling from the same height, the mass is going to be the same, the change of velocity is going to be the same. So, if the mass is the same and the change of velocity is going to be the same, well, then the change of momentum is going to be the same. In which scenario does that person experience a larger impulse? Well, if the change of momentum is the same, the impulse is the same, because those are the same questions, right? Which of these scenarios does the person take a longer time to come to rest? Well, it's going to take a longer time to come to rest with that bungee cord. And in which scenario does that person experience a larger force? So it's going to be that static rope, right? So that's why it used to be a way that people would be executed, because it applies a large force to the neck, just like in that movie The Mummy, from that still up there. And like I said, don't worry, Hollywood movie, and he survives, and he goes on because he's the hero of the movie. So pretty good movie. Um, so which variable does the bungee cord increase? It's going to be the time interval that force is applied. Which variable does the bungee cord decrease? Well, it's going to be the force that person experiences. So just like in both these scenarios, assuming it's the same person falling from the same height, well, that bungee cord is going same mass, same change of velocity. End result is the same. They come to rest. But what that bungee cord does is it stretches that force out. It spreads that force out over a longer period of time, so the force experiences is a lot smaller. All right, so now let's use that to answer these questions. So we know that the bottle, assuming it's falling from the same height, it's the same bottle, is going to experience the same change in momentum, same mass, same change in velocity. So which of these does experience a larger impulse? Well, same in both scenarios. Now compare and contrast the bungee cord. Let's see here. Does the bottle experience a longer time to come to rest? It's going to be the bungee cord. It's going to take a longer time for that bottle to come to rest. So which variable of impulse does the bungee cord increase? Well, it's going to increase the time interval that force is applied. And which variable of impulse does the bungee cord decrease? It's going to decrease the force that's applied over that time interval. So now let's look at this one. Why do cars have airbags, right? So this is a video of airbags, if you wanted to watch that. So let's look at that, right? So we know that either way, the change of velocity is going to be the same. They come to rest, right? Which does that dummy experience a larger change in momentum? Same dummy, same change of velocity, same change in momentum. So impulse is change in momentum, so same impulse in both scenarios. But which of these scenarios does that dummy take a longer time to come to rest? Well, it's going to be that airbag. It's going to take a longer time to come to rest. Well, which of them does it take a large, or does the dummy experience a larger force? It's going to be that steering wheel, right? That's why that causes a lot of injuries. So the variable that airbag increase is going to be the time interval that airbag or that the force is experienced. Which variable does the airbag decrease? It's going to decrease the force that's experienced. So same mass, same change of velocity, same end result. However, hitting that steering wheel is going to be a large force, small period of time. But what that airbag does is it spreads that force out over a long period of time. All right, so let's switch gears and talk about how can you use your knowledge of. Oh nope, that's the wrong one. This one's talk about why do that's just a typo. So that's a additional one, like how boxers take a punch by leaning in and leaning away. But what this is supposed to read is, well, why do lacrosse players use rackets? So let's look at somebody throwing a ball. So in this one, I had somebody throw a ball with the wrist, somebody throw it with just their elbow, and then somebody throwing it with their whole body. So in which of those three scenarios does the ball have a larger mass? Well, it's the same ball, right? I just haven't used the same ball. In which of these scenarios does that ball experience a larger change of velocity? It's going to be the whole body. It's going to be the whole body. In which scenario does the ball experience a larger change of momentum? Well, same mass, larger change of velocity. It's going to be the whole body. In which scenario does the ball experience a larger impulse? It's going to be the whole body again, right? Because change of momentum is impulse. Which scenario was the impulse applied the longest amount of time? So it's going to be the whole body, right? And that should say force. Was the force applied for the longest time? And if this person wants to throw the ball as fast as possible, what variable would they want to try to maximize? Well, yes, they want to try to maximize the force that's applied to the ball. However, what like the reason why, even though your wrist is pretty strong, but when you throw it with your wrist, you're only applying a force for a very short amount of time. You're using your elbow, you're applying it for a little longer time, using your whole body, you're applying that force over a long period of time. That's why it goes faster. That's why they teach baseball players to follow through on their pitches so you can apply that force for the longest amount of time. So that's why um, like lacrosse players have rackets, because what that does is it extends the amount of time that force is applied, right? And also, like yeah, that's what that does. And some sports, a lot of sports have that. Any sports that have that'll apply the force for a longer period of time. All right, so now we're going to switch gears and introduce our next topic, which is collisions. So the question is, what happens to momentum during a collision? So in order to answer this, we looked at coin collision. So this is just a very simple lab that anyone can do at home. So all you need for this is a large coin and a small coin, and all you have to do is place the large coin on the table at rest, put the small coin under your finger and slide it into the large coin. Explain what happens, which coins are moving after, and or after the collision, how fast, and in what direction. Then what you're going to do is you're going to switch, and you're going to have the small coin at rest and slide the larger coin in. So it doesn't matter what coins, as you have one larger than the other. So what you should notice, if you slide the small coin into the large coin, that small coin should stop or bounce back a little bit, and that small or that large coin should move a little bit. Now, if you launch the large coin and the small coin, that large coin just sort of barrels right through the small coin and keeps moving. So let's just answer these questions, and this is just sort of on observations. Well, which has more momentum, the small coin at rest on the table or the large coin at rest on the table? Explain your answer. Well, they both have the same momentum because remember, momentum is dependent on mass and velocity. So if they're both at rest, they both have the same momentum, which is zero. So which has more momentum, the small coin sliding on the table or the large coin sliding on the table? Explain your answer. And then this is the key where you can answer it. Assume both coins have the same velocity. So that large coin is going to have more momentum because it has more mass and they're moving at the same velocity. So it's going to have more momentum, like more oomph. All right, and then the last one says it will explain what happens to the momentum of the coins during the collisions, right? So when you're sliding, what happens? Well, what you should notice is that you should be able to say, well, it looks like some of this momentum is transferring from one object to the other. All right, so once again, this has been momentum and impulse and a little introductory to collisions. So as just a final thought, remember there is too much unknown in the universe to take a break from learning. Get out there and question everything.